ladies and gentlemen, good afternoon. Nice to see you again. We have had a little bit of lapse in our seminars, and now we are back. Now, Mr. Jeakle has been involved with the design and construction engineering of a wide variety of bridges over the last 25 years, with a focus on cable-stayed and other complex bridges across the United States, Canada, and India. He received his bachelor's degree in civil engineering from Michigan State University and a master's degree from the University of Illinois. Mr. Jeakle works for McElhanney Consulting Services as the bridge practice lead and manages the company's Tampa office. Please join me in welcoming our speaker.
All right, as we said, I'm going to take a little bit of an international flavor of this thing and give you a glimpse into the world of India and some of the work that I do over in India. I've been working over there for about 8 years now, off and on some major projects. And I've got some interesting stories to go behind it. And I'll start off by saying that part of this slideshow is stolen from one of my co-workers that we presented in France last year. So he's in London right now, so I can't take all the credit for it. But then again, I can't take all the blame either. So we're just going to go over the location of the project, give a little bit of context as to where the project is, talk about a new type of bridge. It's not totally new, but it is fairly innovative and it's fairly recent over the last 2 decades, which is very new in the bridge world. So we don't have any in the Tampa Bay area or in Florida in general. So I'll talk about the bridge in particular that we're working on, the Veer Kunwar Singh Bridge in continent India. Talk about some construction, show lots of pictures from construction because pictures are always a lot more fun to look at than listening to me. So we'll start out with India in general. So essentially, they are in the midst of a major modernization and development of their infrastructure system right now. Very similar to what we went through right at the end of World War II back in the 1950s and the 1960s, where we invested a tremendous amount of money in our interstate system. And it was this that we realized it was not only for military purposes, but it also gave a lot of economic growth potential. Well, India is about 60 years behind us in this regard. They're just now, over the last 10, 15, 20 years, expending huge sums of money to get an infrastructure system in place. It is extremely difficult to get around this country in an efficient way. There's roads everywhere, and they've got probably the most roads that anybody, some 3 million miles of pavement, but they are not what you would need to get your good moved around the country, and that's what they're trying to fix at this point. So the area that I'm dealing with is in green over here, and that's the state of Bihar. It's up in the northeast corner, just south of Nepal. It's sandwiched between the Ganges River, which is in red, and Nepal above it. It is one of the more densely populated areas in India, and that's saying a lot because this whole place is densely populated with 100 million people living in that little area. And it also has the lowest per capita income in all of India and a significant part of the world. So here's the density map of India. So we are right here, this blue dot. This is the whole area here that's extreme density. And then over here, you'll see this is the listing of states in the per capita. And the state of Bihar is right down here on the very bottom. And it's hard to read, but they have a per capita income of $590 per person per year. That's pretty darn low compared to up at the very top of that, which is the Goa region, which is 5,500, so about 10 times more prosperity in Goa than in the state of Bihar. It is an extremely poor region. This is zooming in on the site location. That is the Ganges River flowing through there. It's just a meandering river that dries up, floods, dries, floods, but we are just to the west of Patna. Patna is one of the major cities. My guess is a decent-sized city over there has 8, 9, 10 million people. We would call that a mega city, but to them, it's just another spot on the map, another city, although it's a pretty good sized one. So that's where our location is that we're going to be talking about, the ERECTION Bridge, crossing over the Ganges River just to the west of Patna. Zooming in on the crossing, this is everything you see colored here is a bridge. The red, purple, and yellow. The purple is the navigation span. That's the major part of the river. It's dry in this photo pretty much, but it floods out frequently to get to the full width of the banks of the purple. That 1,900 meters of navigation span is the bridge that I'm going to be talking about, the Veer Kunwar. Other people designed the red approach stands on the north end and the approach stands on the south side over here. It's important to know that, even though that this is the river banks here, this also gets flooded and routinely every year will be full of water. So the whole river goes from a couple hundred meters wide to almost 3 kilometers wide during the monsoon season. Here's just a couple shots of the same location. Dry day and a not so dry day. So it gives you an indication of kind of the ranges that they have to deal with on the Ganges River, because it dries up significantly outside of the monsoon season. When the monsoons roll in, that river starts roaring and floods massive areas, and people generally get surprised by it every year. And you'll see that later in some of the construction photos. We've got equipment sitting out in the water as it got flooded. All right, just a little bit more context. This is the actual site here, looking from the end of our bridge, looking across the Ganges River. Just a big, vast plateau in this area, very sandy region. The river shifts around a lot. That's why this navigation span is so wide, is this river just kind of meanders around and shifts wherever it wants to go. When these monsoon rains come through, that river will not be where it was last year. It moves frequently. Some more sites, just the local culture there is everybody makes their own boat, gets across the river in boats. There's not many bridges across the river right now. There's only a handful of bridges across the Ganges River in this region. So everybody relies on boats and little ferries to get back and forth across the river. This is a very common scene. Is you come to the river, they get some lumber, they build their boat on the side of the river, launch it, get to the other side, and they will ferry people back and forth, and they just build their boats right there on the riverbank. So this is, they're building their infrastructure system now and trying to get it a lot more modern and flowing. They do have a lot of infrastructure there. It is kind of old. It is worn out. There are a few major river crossings, but they're few and far between. And it makes getting from point A to point B, it can be 20 kilometers away. But that sometimes is a 2-3 hour excursion to get that 20 kilometers. It's very challenging because you'll have one bridge like this that serves a several hundred kilometer area. And I have been myself stuck on these things in traffic jam. There's an accident at the end of the bridge or something's happening. And you just sit there for 4, 5, 6 hours before traffic is clear out. They do have some more modern structures, but again, this is part of their issues. This one was only built back in 1982, so it's less than 40 years old. But this picture's a little bit old. The reason I know is right now they've torn this bridge down, at least down to the water line, because it was built so poorly, designed so poorly. This is a photo not too long after it was open, and you see it's cracked up everywhere. Some of the stems are settling, and it's just, within a year of this bridge being open, this is a massive crossing of the Ganges River. It was undergoing major rehabilitation and fear of collapse. They've been working on it for the last 40 years, and now they finally decided just to tear it down. So that kind of plagues their infrastructure. It's just poor construction in the past. They do have some nicer, more modern bridges. So, you know, I started off with saying that we're going to talk about a new type of bridge, an EXTRADOSED bridge. And what an EXTRADOSED bridge is it's somewhere between a regular beam bridge, which is stuff that you see out there all the time. It's just a standard bridge, no cables, no nothing, just a girder, to a cable-stayed bridge, which is like the Sunshine Skyway, which is good for longer spans. And so the beam bridge, we really only do these things up to about 500 feet in length is practical. Anything longer than that, it gets kind of tough to be building in that fashion. The cable-stayed bridge is pretty efficient when you start getting up around 1,000 feet, 2,000 feet, when you've got some significant spans across. Well, what do you do when you're in this range between, say, 500 feet and 700, 800 feet? And that's where we've got this EXTRADOSED type bridge. It's kind of a girder, but it also has stay cables on it. It's squat little towers, a few little cables. The girder's got some decent stiffness, whereas the girder up in the cable stay is a very soft, flexible system. So this is the gap that we're kind of filling, and we started these things, you know, a good 30 years ago, 20 years ago, and we're starting to see them pop up around the world as they fill this gap between the two traditional bridges of a cable stay and an EXTRADOSED. This is the first concept of an EXTRADOSED by Mabry in 1988. It never did get built in Switzerland, but this was the first time somebody came up with this idea of doing something in this gap between a cable stayed and a girder bridge. It wasn't until 1994 that we started to actually build these things. This was the first one in Japan. They've built probably a good 20 or 30 in Japan since then. But they're kind of the leaders of taking this idea and making it very efficient and just another tool in the bridge designer's toolbox. So now this is the Veer Kunwar Bridge. This is the bridge that I'm talking about over the Ganges River. This is a day where there's actually a lot of water out there. Currently, this is the world's longest EXTRADOSED bridge. Let me back up one thing. Is the name EXTRADOSED. Somebody came up with it a little while ago. I have no idea who. But the term EXTRADOSED comes from the word extrados, which means the exterior or upper curve of an arch. How that pertains to that bridge, I have no idea. But somebody thought it did and felt that was a good name. So I don't understand it myself personally, but I still reference it as an EXTRADOSED. I'll take your word for it. That's a good idea. So getting back to the world record is the Veer Kunwar Bridge. It is 2 kilometers long, 1.9 kilometers long, back-to-back EXTRADOSED spans, or 16 towers marching across the river. Unfortunately, I'm only going to hold the record for about another year because there's another bridge under construction just up the river that's 5.5 kilometers long, which is quite a bit longer than this one, but at least we got the record for a couple of years. This is what the bridge looks like in technical drawing terms, 1,900 meters long. Each spans 120 meters or 394 feet for each span. There's 16 piers or pylons back to back. Very regular all the way from end to end. You'll see, we'll talk about this later, we've got these expansion joints at every third span along the length of the bridge. That's to allow this bridge to expand and contract during thermal temperature changes. When this bridge goes through, like, say, a 50-degree Fahrenheit change, this piece of the bridge right here will expand maybe 4 inches and then contract 4 inches during a 50-degree cooler day. So we provide relief joints at every 360 meters to allow this thing to breathe, essentially, and not. If I tried to make it continuous end-to-end, I'd be pushing this pier on a hot day, I'd just knock the pier right over, quite simply. So we provide relief expansion joints along the length of the bridge. And I'll kind of show you how those work a little bit later. Yeah?
So, what do the first pillars are closer to the first ones?
The first span over here? Yeah, that's a good question, because the way we build this thing, we cantilever out. We start here at the pylon, and we cantilever out to here. And we do the same thing here. We meet in the middle, we stitch them together. Well, I've got no pier over here to meet out. So I build out as far as I can, I stop, and I put a pier underneath that end. So always at the end of the bridge, you always have a span that's shorter than the rest of them. About half the length of the other spans. Somewhere in that range. So this is what a little piece of the bridge looks like. It is a concrete box girder, which we have a lot of these around the Tampa area. The reversible lanes on the Selman Expressway are a concrete box girder. The Sunshine Skyway is a concrete box girder. So it's a pretty common form in Florida. We've got a lot of those bridges. So we've got a pylon in the middle of the roadway that's about 18 meters tall. Some stake cables, 5 stake cables off of each pylon. Here's the blade columns underneath there. This is the foundation. So we're about 70 meters from water line to the deck level. So not too far up in the air. That's a little bit better view of what the cross-section looks like. It's got 2 lanes of traffic heading northbound, 2 lanes of traffic heading southbound, a footpath or a sidewalk on both sides. This gap in the middle is where the stake cables anchor in here below the deck, and they go through the deck and up to the pylon up at the top. These pieces of the bridge that we build them in precast segments are about 10 feet long, each one. And we build them off-site, we ship them there, and we glue them all in place. So I'll show you that when we get into the construction photos. So now we're getting into construction. That's not me. I don't know who that is in there. So they have a different outlook on safety over there. Actually quite surprised to see them with hard hats. Most of the time they don't have hard hats. Flip-flops, a lot of flip-flops, guys working in shorts, no gloves, no safety goggles. You compare that to any site on the U.S. In the U.S. we all have the Jeakle orange vests on. We've got gloves, we've got glasses, hard hat, boots, steel toes, steel shank boots, pants. You see a couple photos, guys don't have shoes, don't even have flip-flops on. And it kind of gets back to the point that it's not that they don't care. Remember, we've got a per capita income $590 a year per person. Having shoes sometimes can be a luxury. And all right, we'll start with the dirt, the foundations. This is a river that shifts a lot, it moves a lot. Where it is this year, it will not be next year. Hopefully it stays somewhere underneath our bridge in the 2 kilometers that we provide it, but we do not know. We do know also that the sand is going to scour around and shift and move. And you actually may end up getting scour holes around some of your piers. Some of these scour holes may be up to 100 feet deep. Just that much sand gets shifted around on these rivers during the massive flood stages. So these foundations that we're talking about that we're sinking are very big. Essentially, it is a ring of concrete that is 33 feet in diameter. The walls are about 5 feet thick, and it gets something down about 160 to 170 feet deep. It is pretty much a building unto itself, and we have these at every 394 feet across it. So in this view, you can kind of see a lot of the foundations that are partially sunk, and I'll show you kind of how these things are built. We used to do this in North America, but then came the 1900s and we decided to stop doing them. You go to the Brooklyn Bridge, you go to the Golden Gate, you go to the Leeds Bridge. Some of those massive bridges that we built back in the 1800s, early 1900s, 1940s even, we used to use these well foundations, these sunken caissons. But I guarantee you cannot find a contractor in North America that would know how to put one of these things in today. They just do not know how to do it, nor do they want to do it. It's very expensive. But the Indian contractors are extremely skilled at these things. they're good at it. They use them quite a bit over there. Although they're starting to learn some new technologies and starting to learn some of the techniques we use for foundations in North America in making the switch over. And part of that comes from people like me from outside of India bringing in technology to them and pushing alternative ideas to get away from some of these expensive things, get them out of their comfort zone, get them into something that's a little more efficient and easier to build and easier to maintain. So it's a bit of a technology transfer there. This is just a rendering of what these caissons or well foundations look like. We were essentially casting these things in concrete rings, maybe about 20-foot high lifts. And so you cast the 3D concrete at ground level. Once you get it cast, you actually start digging away the soil inside it, and it just naturally sinks. And it adds under its own weight. And if it doesn't start to sink under its own weight, you stack weights on top of it until it sinks and gets back to ground line again. Take all your weights off, you cast your next section on there, and start digging out in the middle, and it sinks. And you just keep repeating that process until the thing gets down to the founding level that you want, which is, in this case, we're down at about 170 feet from the ground line down to the toe of the cutting edge of the caisson. But as you can see, we're just reaching down there and clamming out soil until it just sinks under its own self-weight. The challenging part is to dig appropriately so the thing doesn't tilt and tilt. They do have a tendency to do that, and that's why I say it takes a lot of skill to put one of these things in. If somebody from North America tried this, it would be an absolute disaster. These guys are very good at it. So here's a shot of one of the wells going in. It obviously was not sinking under its own weight, so it's being helped a little. You just keep stacking weight on there until it goes in. It's a very brute force way of building a bridge. But that's what they excel at, is brute force way of doing it. They know it works. Yeah.
What have you replaced this with?
We use individual like drill shafts or driven piles that may be 2 or 3 meters in diameter. Just small little ones where we just drill down, we pull our drill out, we put some rebar, and we dump concrete in there. And we move over, we drill another one, so we'll put 20 of them or so. But they're very easy. And if you go down to the Gandhi Bridge right now, or Gandhi, you'll see the big drill rig out there. And he's just drilling. He'll drill down 60, 70, 80 feet, pull out all that soil and leave a hole there. And put a rebar cage and then dump it full of concrete. So that's a drilled shaft. That's what we use 90% of the time here in the U.S. We don't ever do something like this. We use much smaller elements, but lots of them. Yeah.
Now, this one's a lot more expensive, harder to put in place, but is one stronger than the other?
This is extremely strong. And the benefit of this one is it deals with the fact that all that soil can be scoured out, and we lose all that supporting strata, and now this thing's just freestanding for 100 feet. And it's a really robust system. Our systems are the drilled shafts, because I'm designing another bridge over the Gandhi right now, and I'm looking at both of these alternatives. I'm looking at piles, and I'm looking at sunken caissons. And those piles are very tough to make work. I mean, they're 100 feet of scoured out material. So, yeah, so they're really, really robust after you get it in place. Yeah, that's kind of a little bit better. You just kind of keep building up, shutting it down. When we get down to the bottom, we excavate a little bit more. We cast the concrete plug in the bottom. We cast a plug up at the top. So now you've got a silo essentially, and we can build our columns and our piers on top of the upper lift there. So now once we get the top of that thing, now we can start building our columns, and that's what you see On the left there is our columns going up all the rebar. And now you're at least working in the dry. You're up above the water, you're out of the dirt, and things get a lot more predictable at this point. You get up to the top of the column, and then we cast the first part of our superstructure, which we call a pier table. That's the piece that's up on top of the columns. It's cast on false work. You can see all the scaffolding and everything that rests. This is the top of our piece on our well foundation down here. This one happens to be on dirt. And we just put all the scaffolding up and all the formwork up there and cast that guy right in place. And that may take a good 3 to 4 months to cast that little piece of bridge in place. Once that's cast in place, right in situ, we will actually start building out the bridge from there using precast pieces. We're gonna build pieces off-site, ship them in as completed sections of the bridge, hoist them up, glue them to the face, put some tendons in there some steel rods in there to hold them in place, and just slowly work our way out and figure it out. But we're not bringing any fresh concrete in. Everything is precast concrete off-site. So this is kind of our starter section here, our pier table. So I talked about those precast sections that they're making. And again, this is the exact same procedure that we're using on the Selman extension down in Gandy right now. Is they're precasting some of our segments in the yard off by the port area, and at night we ship them over to the Gandy Bridge and we erect them at night. As you can see, here's one segment in the background. It's, again, about 10 feet long. Here's the next segment that we're getting ready to put all the rebar in there, all those tensioning tendons, and once we get it all tied in, we'll take this bulkhead form over here, stand it up on this end, and you're going to cast a new segment between the form on this face and the precast segment on the back face. It's called match casting. That way those two segments are perfectly matched to each other. Every little imperfection in one has got an equal and opposite imperfection in the other one. So we call that the match cast segment in the back and the wet cast segment in the front. Here's another view of it from the other side. We're looking at the previously cast match cast segment. And these segments are 2.4 meters tall, so that's about 12 feet tall or something like that. And there's the forms for the wet cast segment. We just cast. Once that cures and dries, we break the forms off, and the forms ahead 10 more feet, tighten back up, cast another section. We just keep walking down this area casting segments. So that's kind of what it looks like when after you cast the segment and it dries and it cures for a couple days, kind of separate them apart a little bit and let them, they just, essentially we'll sit here and cook for 3, 4, 5 months until they're done building the piers out in the water. This is going on while the contractor's out in the river putting in his foundations, building up the columns, doing the pier table. This is happening off on a different project site or a different site a little ways away. These segments weigh, those are metric tons, so it's about 100 US tons to 110 US tons per segment. That's 65 feet wide, about 12 feet tall, and about 10 feet long, each one of them. Pretty good chunk of concrete to be picking up. And this yellow piece of equipment we call a straddle carrier. You'll see it in a couple pictures from now underwater. It's not supposed to be underwater. So now that we've got all those segments cast, we have to transport them to the site because we have to bring that big 100-ton piece of concrete directly under the bridge so somebody up on the bridge can reach down, pull it up, glue it into place. We've got to transport it directly under where we are. The monsoon season, the wet season plays a big role in this, and it's a very challenging aspect of working in India as the monsoons affect the entire country just at different times. And it's something that just really wreaks havoc with construction schedules. Basically, the monsoons start in June with the heavy rain, so by July, we pretty much getting inundated every day. And it will last until sometime in early September and peter out by the end of September. It's not the monsoon that's challenging, it's actually the transition periods between the dry and the monsoon. And the monsoon and the dry. That's the challenging part. When I have water out there, not a problem. I can bring things out in barge. When it's dry, not a problem. I can just drive right out there. It's when the water's in between those two that it really makes for a challenging assignment. So this is what it looks like in the dry season. There again, that's a dry season going on, obviously. And pretty easy just to drive equipment around down there. So we just drive the truck, drive the segment directly underneath the cantilever where we need it. They send down some high-strength rods and connect up, and we hoist it right straight up and glue it onto the cantilever tip. So you can see the hoisting equipment at all the locations. Pretty easy. Then it gets wet. So again, it's not good for the equipment, but this is monsoon season, and this is the other extreme, it is the wet season. And it's actually, it's bad for the equipment, but it's actually nice for other aspects where I just float the equipment around. Now I don't have to drive, now I just put it in a barge and float it wherever I want to, and hoist up. It's actually easier to maneuver it on the water. As long as you've got reasonable water depth, you can get it to exactly where you want it to. So this is in the wet season here. Then comes the in-between seasons. Don't have enough water, but yet you have too much water. So what we don't see in this photo is the other wheels of this straddle carrier are actually sitting out in the water. So he's sitting there after he's done putting the second on. They can't do anything with him until they figure out a way to get out of there. The water's not deep enough for the barges to come and push or the tubs to come and push the barges around. So these guys are fairly innovative. They'll basically just put a backhoe on this thing, and he just reaches down, grabs, and pulls himself forward. It's you show that to a U.S. construction worker, and he's like, can't believe what he's seeing. But the Indians, it works great for them. It allows them to keep going. Their barge is completely grounded out. It's just dragging sand behind him, but he's able to crawl along and keep working during these in-between seasons. But it's a major problem on the Ganges River. There's our straddle carrier. That was a bad day. Somewhere underneath there's segments and wait for the water to go down. Not much you can do. All right, so here's the means of erecting these segments. So here's the pier table that we have in place. We've already got one segment that we've attached on this side, one segment we've attached on this side. This will be the second segment and the second segment. So they're basically hoisting gantries, lifting gantries that are bolted down to the bridge deck up there. And they're capable of lowering down the high-strength rod, grabbing a hold of concrete, and hoisting it right back up in place. That's a shot of what that piece of equipment looks like. You can see that it's kind of tied down to the bridge deck. Behind it, there's some high-strength rods that go to the concrete deck. These are actually the state cables, the first couple of state cables that have been erected up there. Once you bring a segment in place, you hoist it up, you get it into position, we apply we call it a glue, but it's not technically glue, it's an epoxy bonding agent. And this is the same way we apply it in the U.S. as well, just by gloves. You just take it, glue it on your hand, and just smear it onto the surfaces about a 1/16 of an inch thick. Exactly what it looks like. It's an extremely messy operation to do this. But you basically butter up that whole surface, and once you get it fully epoxied, here's what it looks like. Here's the guy with no shoes on the inside. Cleaning up the web, getting that spread all over the web. Once you get the surfaces all glued together. You basically squeeze the two segments together and with some high-strength rods, and you press them together to squeeze that epoxy out. That epoxy, it is technically a glue, but we don't count on it structurally. It is just there to lubricate the segments so they slide together nicely and to waterproof that joint. You can see where the epoxy is leaked out through the joint. As you squeeze it, it comes oozing out. These are the rods that we put across from segment to segment, and we pull them together and basically let that epoxy cure overnight, and then we do it again tomorrow. So every day we'll put up one of these segments and build another 10 feet of bridge per day. Getting to above deck. This is our pylon. So this, we were looking at the top of the bridge deck, and that's going to be a concrete pylon that goes about 18 meters in the air. This is looking down the length of the bridge, and you can see some of the holes in it, and it's actually a saddle. It's a pipe that goes through the middle of the pylon. So the stay cable strand starts inside the box girder over here, comes up through that saddle, goes down the other side, and into the box girder on the far side. And about 18 meters tall. A very simple element, just a rectangle, solid concrete. Oops. Yeah, it's just another animation showing you just keep leapfrogging your way out there until you get far enough out, then you install a stay cable behind you. See the first stay cable get installed there. You get in, you leapfrog a couple more steps forward, put another stay cable in behind you. These cables are fairly short, they're fairly shallow, they're only at about 19 degrees. Where a true cable stay bridge, like the Sunshine Skyway, they're up quite a bit taller. They're at about 25 degrees or so, so there are a lot longer stay cables on the Sunshine Skyway. These are relatively small little cables, and they just go maybe halfway straight through the pylon and down the other side. So this is a view inside the box girder here. And each one of the stay cables on this bridge, there are 61 individual strands. And each strand is probably about the size of my thumb. They're very high strength strands. Each one is capable of holding about 60,000 pounds apiece. So when you put 61 of them together, that's a heck of a lot of force. You know, essentially, each strand can support probably 7 SUVs. So 7 times 61, that's a whole mess of, that's a parking lot full of SUVs that cable can hold. So this is the cable that's kind of popping out of the bridge deck, comes through a pipe, goes up to the pylon and back over to the other side, and they're stressed inside the box girder to provide force. I had to get a shot of me in there actually. So that's me in the middle there, doing my inspection. As an engineer, I basically drive a computer and a desk and rarely get my hands dirty. I do have to go out to the sites a lot and inspect things and look at stuff, but they generally don't let me touch anything. It's probably wise. All right, just the animation where it just kind of keeps going out, just keep bopping out there and putting in stay cables behind you. This is the relief joint I told you at the middle of at each one of these expansion joints. So we have these in every bridge we build, there's always expansion joints. They're normally at the beginning and end of the bridge. When you go down the highway, you'll see that they're at the beginning of the bridge and at the end of the bridge. We generally don't do too many along them. When you get something that's 2 kilometers long, putting it at the beginning and the end doesn't really cut it. So we've got them at every 3rd span. So again, this is the center line of the span here. It's 60 meters to that pylon, 60 meters to that pylon. There's actually a gap between the 2 structures. They're not physically touching at all. There's probably about a 2-foot gap there. The only thing that's between those 2 is we put a steel beam, a shear beam inside there that basically makes those two cantilevers behave. They're not allowed to deflect individually. That steel beam makes them move together. So even though the bridge is able to expand and contract this way to deal with the thermal, it can't move this way relative to each other. We want them to, nothing worse than going down the road and having a 1 foot bump in front of you. So these allow it to open and close, but not go up and down relative to each other. So this is how this is a picture of it being built, and the beam is right there being shoved inside the box girder. So we have the cantilever out of way, stop, shove the steel into the box girder, and then finish off the cantilever and then pull the thing across that open point. This is a little bit better animation that you can see with the crane, the double pick crane, where we're taking it and stuffing it inside the box and holding it in there temporarily until we can drag it out and make it cross the span. That's just a close-up of what that beam looks like, and this is the gap between the two cantilever tips, a couple foot gap there. Lots of bolts, lots of big thick steel plates there. Very tough stuff to work on. There's those beams, they just got put in there, hidden back out of the way. So that's the finished bridge right there. Obviously, high water. It turned out good. It's, to us, this is the type of bridge we don't have in Florida. We don't have anything like this in Florida yet. We've got bigger bridges in Florida, but not this EXTRADOSED type. India's doing a lot of these types of projects, and they're using, this is a high technology bridge that they're building here that they're doing. They still have, and they're still back in the old days with their foundation, but we've convinced them to use some high technology bridges, at least once you get above the water. And it's helping them, because they're building so much infrastructure out there now that they're very interested in bringing in foreign consultants like myself to kind of bring the technology that we use in North America to them and introduce them to their country. And we work with the local Indian engineers and a technology transfer with them. We generally partner up with them, team up with them, and facilitate that transfer of technology to the local Indian market. Another view. As part of the construction team. And it's hard to underestimate what this really means to the local community when you get a new bridge that hasn't been here for 100 kilometers up and down the stream. It's the difference between a 10, 12, 15-hour drive to get to somewhere and the ability to walk across the bridge should you not mind walking 5 kilometers. But the ability to get across that river now is immense.
How long the bridge is going to last?
It's supposed to last, the design life is typically about 75 years. And that's the same as in the U.S. Realistically, if they don't do much maintenance, they'll get 60 years out of it. If they do a decent amount of maintenance and do what they're supposed to do, they can get 100 years out of it. They tend to become functionally obsolete before they become structurally obsolete. In other words, they don't have enough engines. It's overcrowded. We have to tear down and build a wider